Hello students. So, this is the second part of the lecture on isolation and characterization of proteins. So, in the last lecture I talked about purification of proteins. So, we saw that we can purify proteins by two methods. One is we can have an affinity tag on the protein, which makes protein purification process much simpler, and the other is when we do not have any affinity tag. In that case, we need to purify protein through multiple steps. In some cases, it is not advisable to put an affinity tag such as the 6-histidine tag, because it may interfere with the folding of the protein, or it may interfere with the function of the final folded protein. So, in such cases, untagged proteins need to be purified, and then multiple steps of purifications are required. So, in the last lecture we saw that after protein purification we have this final protein in our hand. So, once we have this pure protein in our hand, we have to ask ourselves several questions. So, the first one is that whether the protein that we got is the correct protein. Is it the one that we intended to purify? Because what you will see is just a colorless solution, okay? And just by looking at it, it is very difficult to tell whether it is the correct protein or not, unless your protein has some color or fluoresces under UV or some other characteristics which make it easy to identify. So, the first question we ask and we have to ensure is that we have the correct protein in our hand. Then we need to ask how much did we get. So, from purification, if it is affinity purification, then the yield is normally high because the number of steps of purifications are less, but if it is purified by multiple steps, then the yield goes down. So, in any case, we need to figure out what is the exact amount of protein, purified protein we have in our hand, so that we can plan the subsequent experiments. So, typically the protein concentrations are given in these two units. One is millimolar. So, millimolar is the number of millimoles that are present in 1 liter of your solution. So, number of millimoles of your protein in 1 liter of solution. The other unit that is very frequently used is milligrams per ml. So, the number of milligrams of protein that is present in 1 milliliter of solution. So, somehow we have to estimate the concentration of protein in one of these two units, and these are easily interchangeable. The third question that we have to answer is whether this protein solution that we have is a homogeneous mixture, because in many cases proteins tend to oligomerize. So, some proteins like are present as dimers, some proteins are present as tetramers, some proteins can also form higher oligomeric states, and some proteins also tend to aggregate. So, we have to figure out whether the solution that we have is a monodispersed solution or it is a polydispersed solution, so that it has monomers and higher oligomers, and that will determine how we design the subsequent experiments. Another aspect of protein purification and subsequent characterization is to determine whether the protein that we have at the end of this long purification protocols is whether it is correctly folded or not. Because we are going through multiple steps of purification, and it may so happen that all these mechanical agitations can unfold some molecules. So, what you might end up is having a mixture of correctly folded and unfolded proteins, and remember that unfolded proteins will also be soluble. They do not always tend to precipitate, and if you have done your purification through affinity chromatography, then the affinity tag will be present in both folded and unfolded protein, so that both will be purified, and you might end up with a mixture of folded and unfolded protein. So, we will have to figure out a way to tell whether we have 100% folded protein or if there is a mixture of folded or and unfolded protein, and then separate them so that the final solution that we have is correctly folded protein. And finally, we have to determine whether the protein is functional. So, that will be based on some assays. If it is an enzyme, we will have to do enzyme assays. If it is a ligand binding protein, we will have to design ligand binding assays to ascertain that the protein is correctly folded and the protein is functional. So, in today's lecture, these are the topics that I will go through. I will talk about the information that you can obtain about a protein from its primary sequence, and you can use that information to design subsequent experiments. How do you determine the folded state of the protein, and what are the oligomeric states of the protein, and finally design some functional assays to ascertain that the protein is functional and also correctly folded. So, these days we mostly know the sequence of our protein. It rarely happens that we work with a protein whose primary sequence is not known. So, I will assume that the protein that you are going to work is its primary sequence is known. So, if we know the primary sequence, there are several properties we can calculate directly from the primary sequence. The first one is the molar mass. So, if you know the sequence, the molecular mass of each amino acid is known. So, you simply add the mass of all those amino acids and you can get the molecular mass of your protein. It can be easily done through various programs that are available online. One quick way of doing this is, if you know the number of amino acids, you can simply multiply that with this average molecular mass of each residue. So, if you have 100 amino acids, then you multiply it by 110 Dalton and you will get 11 kilodalton as the molecular mass of your protein. So, we have some idea about what is the molecular mass of our protein. Now, using these two techniques, one is the size exclusion chromatography and the other one is the SDS page electrophoresis, gel electrophoresis, we can determine the purity as well as whether we have the correct protein. So, you have already seen these two techniques. This, in case of size exclusion chromatography, our protein of interest is 13 kilodalton because it has 117 residues, and multiplying it by 110 Dalton, we know that the molecular mass should be, the expected mass is around 13 kilodalton. The peak that comes out is more than 90 ml. So, these positions are highly specific to the size of the protein. Larger protein molecules elute earlier, smaller protein molecules elute later. So, this peak position corresponds very well to a protein of mass 13 kilodalton. Similarly, in case of SDS page gel electrophoresis, these fractions that were collected from this peak were run into this gel, and you can see that it is a highly pure protein. There are no bands up or down, and these bands correspond to a range between 10 kilodalton and 15 kilodalton. So, these are the molecular weight markers, the standard known weights of mass of protein, and 13 kilodalton will be somewhere here. So, again using these two techniques, we can confidently tell that our protein has the right mass. So, most probably it is the right protein that we intended to purify. So, the first information that you get from your sequence is the molecular mass, and we can use that to give us confidence about the correctness of the protein that we have purified. The second information that we get from our sequence is the molar extinction coefficient, which is the epsilon value at a particular wavelength. In this case, we are going to use 280 nanometers. So, if you remember Beer-Lambert law, the absorbance of, let us say, a protein molecule can be determined from its molar extinction coefficient multiplied by the concentration of the protein multiplied by the path length. So, this is the cuvette in which you have your solution sample. The light is incident and then it is whatever is absorbed, the remaining is detected. So, from that we get this absorption coefficient. So, A280 is known. If we know epsilon 280, L, which is the path length, this one is roughly 1 centimeter. So, typically it is set to 1 centimeter. So, L is also known. If we know L, we know epsilon 280, we know absorption, we can calculate the concentration of the protein, and this concentration will be again in terms of millimolar. So, to use this Beer-Lambert law, we need to somehow know epsilon 280, and this epsilon 280 can be very easily determined from the primary sequence of the protein. It turns out that out of the 20 amino acids, only 2 and to some extent this third one absorb significantly at 280 nanometers. So, tryptophan is the one which absorbs the most, followed by tyrosine, and if you have cysteine disulfide, then this 2 cysteine amino acids which form a disulfide bond giving you cysteine, then that also has a marginal absorption at 280 nanometers. So, you can see that tryptophan has the highest absorption. Its extinction coefficient is 5500 per molar per centimeter, whereas for tyrosine it is close to 1500 and for cysteine it is 125. So, if you know the number, if you know the sequence, you know how many tryptophans are there, how many tyrosines are there, and you may or may not have this. So, you can simply multiply the number of tyrosines with 1490 and add it to the number of tryptophans multiplied by 5500, and you will get an estimate of your epsilon 280 for your protein. So, once we have the epsilon 280 of our protein, we can use Beer-Lambus law, measure the absorbance at 280 nanometers, and we can calculate the concentration of our protein with great accuracy. So, it turns out that the epsilon 280 of a protein depends on the amino acid sequence. The third important parameter that we can determine for our protein from its primary sequence is the pi, the isoelectric point of our protein. As I have discussed in the last lectures, that pi is something that is very useful to determine the purification protocol. So, you need to know the pi, which you can easily get from its sequence, and you can optimize your purification protocol. Once the protein is purified, we can again use our knowledge of pi to optimize the pH of the buffer in which the protein will be solubilized, and subsequent experiments will be carried out. So, in this case, we want to have a pH where the protein will be highly soluble. So, if the pi is 7, you would want to make a buffer which has a pH of either 5.5, so significantly less than the pi, or 8.5, significantly higher than the pi, so that the protein is either positively charged or negatively charged under these conditions. If you know the pi, you can also run a native page to determine whether you have a single protein or you have a mixture of proteins, where the protein has higher oligomeric states, or there are other degradation products, or the protein has both folded and unfolded forms. So, a native page can be run to determine how monodispersed your protein sample is, the integrity of your protein sample, and again you can run the native page only if you know the pi of your protein. Finally, the optimal conditions of the binding assays can be determined based on the pi of your protein. So, for example, if the protein binds nucleic acid is negatively charged. So, you would want your protein to be positively charged, so that you will choose a buffer condition where the pH of your buffer is less than the pi of your protein. So, how do we calculate the pi? It turns out that there are again only a few amino acids whose side chains are ionizable, and also the N terminus and the C terminus. Now, the pKa of these amino acids and the N terminus and C terminus are well known. So, just by knowing the sequence, we can determine the pi of our protein from using a table like this. So, you can do these things by hand, or you can go online, and there are many web servers where you have to simply put the sequence of your protein and they will do all these calculations for you. So, you will get the molar mass, the extinction coefficient, and the pi of your protein. One such program that is widely used is the ProtParam tool from Xpesi. So, ProtParam stands for protein parameter. So, the hyperlink for this web page is given up here. So, if you go to this web page, you will see a window like this. All you have to do is paste your protein sequence in this box and then click this calculate parameters button. I will encourage you to go online, look up this website and read the documentation link here, because it will give you more details about how all these parameters are calculated. So, put the sequence of your favorite protein here, click compute parameters and you will see an output. I am showing some of the outputs for a particular sequence that I have put in. So, in this case what you see is the number of amino acids. So, you see the number of amino acids is 63, okay, and it also gives you the accurate molecular weight of your protein, which is 7.5 kilodaltons. If we use our rule of thumb, so then in that case we are using 110 daltons. 110 multiplied by 63 will be 6930, so roughly 7 kilodalton. But you see that the actual molecular weight is 7.5 kilodaltons. So, the rule of thumb is good to quickly estimate the molecular weight of a protein, but you should always put the sequence in a program like this and get the actual molecular weight. It also gives you the theoretical PI of this protein. You see the theoretical PI is very high, it is almost 9.6. So, the other information you will get is the amino acid composition. So, it tells you how many alanines, how many arginines, how many asparagines, how many aspartic acid are there in this whole sequence. So, one thing, if you look down here, you will notice that the acidic amino acids are 5 present in this sequence, while the basic amino acids present are 9. So, there are more basic amino acids compared to acidic amino acids. So, it is not surprising that the PI of this protein is more than pH 7. So, the PI 9.6 can be easily explained by the presence of more basic amino acids compared to acidic amino acids. You will get more information, for example, the atomic compositions and the total number of atoms that you have in your protein. So, these numbers can be useful if you are doing NMR spectroscopy to determine the structure of your protein. And finally, one of the most important parameters that you will get is the extinction coefficient at 280 nanometers. So, in this case the protein has an extinction coefficient of 16,960, and you can roughly calculate this number from the number of tryptophans and tyrosines that are present. So, you can multiply 2 tryptophans by 5,500 and add it to 4 tyrosines with, so 4 multiplied by 1490, you can sum that and you will see that it comes somewhere close to this number. So, these programs are optimized, so you will not get exactly the same number, but these are more accurate values. And if you want to know the details of how these numbers are calculated, go to the documentation, you will find the references there. So, at this point what we know is that our protein is correct because the molecular weight matches with the expected molecular weight from the sequence. We know the concentration of our protein and we know that our protein is pure. So, these are based on SDS page, gel filtration and measurement of UV absorption. We might also want to know the size of our protein. So, size in the sense that whether our protein there is only one molecule or a monomer, or whether we have a dimer or we have a mixture of oligomers. So, size distribution of our proteins. So, gel filtration can be used to determine that, but there are also other more sophisticated experiments. One of them is dynamic light scattering, which gives you the size distribution of your molecules in solution. Another experiment that is used, but again these experiments are much more difficult to do than SDS page and gel filtration. So, this experiment is sedimentation analysis. It will give you an independent measure of the molecular weight. It will also tell you the sample homogeneity. size and shape of the protein. So, whether your protein is spherical or whether it has a disc like shape or a rod like shape, this kind of information you can get from sedimentation analysis. And finally, if there is an equilibrium between, let us say, a monomer and a dimer, then the equilibrium constant can also be determined using sedimentation analysis. So, these are again more sophisticated experiments which can be used to characterize your protein of interest. So, this is one example of a protein which exists both as a monomer and a tetramer. So, part of it is, so there is a dynamic equilibrium between tetramerization. So, at the concentration in which this gel filtration was done, some of the protein was in monomeric state and some was in oligomeric state. So, what we see here is 3 peaks. The first peak belongs to the tetramer because larger molecules elute first. The second peak belongs to the monomer, and then this third peak is for degradation products and also some impurities. If we look at the 2 peak intensities and also roughly the area under the peak, it seems like that we have almost equal amount of tetramer and monomer. But keep in mind that tetramer has 4 monomeric units, which means that the epsilon 280 for tetramer is 4 times that of the monomer. So, one tetramer will absorb 4 times that of the monomer. So, it means that if we assume that these two are almost equal, then the concentration of the tetramer is roughly 1/4 that of the monomer. So, you can get this kind of information also from gel filtration. Dynamic light scattering detects the particle size and sample homogeneity. So, again we want to know whether our protein is just a monomer or whether it has higher oligomeric states and things like that. So, the setup of this experiment is very simple. You have your sample in a cuvette like this or a sample holder, and a source which generates monochromatic light, in most cases it is laser, is incident upon your sample, and then the photons are counted in a device like this. So, ultimately what you get is the intensity as a function of time, and you will see that the intensity fluctuates as a function of time. This is because these small particles have Brownian motions. So, they are fluctuating, and that results in the fluctuation of the intensity due to interference and diffraction of the light waves. I am not going to go into the details of the theory, but the very basic of this experiment is that for smaller particles the Brownian motions are much faster. So, the result here you will see is that faster fluctuations, and if the particle size is big, the Brownian motion becomes slower, and then this fluctuation also becomes slower. So, based on these fluctuations, a correlation function is determined which can be used to determine the size of the particle. So, if you have again a monomer and a tetramer, you will get a mixture of signals coming from both the monomer and tetramer, which has to be deconvoluted to get the size of these two particles. Sedimentation analysis is another experiment which can give us a lot of information about your protein size, molecular mass, and also shape. So, the typical instrument that is used is called an analytical ultracentrifuge. Ultracentrifuge because the samples are spun at a very high frequency, a minimum frequency of 40,000 rotations per minute, and it can go up to 60,000 rotations per minute. And while the sample is under this centrifugal force, it is monitored in real time. That is why it is called an analytical ultracentrifuge. A very common way of measurement is the absorption at 280. So, this A280 is monitored throughout the sample for while it is undergoing this centrifugation. The sample holder looks something like this. The center of the centrifuge will be somewhere here, which means that this sample holder is spinning like this. So, this omega will be somewhere in the range of 40,000 rotations per minute, and this is transparent so that UV light can be shown from the top, and you can actually measure the absorption of your sample. So, when the sample is in here and it is rotating at a speed of 40,000 rpm, there are several forces which act on the protein. One is the centrifugal force, which is shown here. This is the force of buoyancy, and there is also a frictional force. So, balancing these forces, what you get is a sedimentation equation like this, and this depends on the molecular weight of the protein. So, you can actually independently determine the molecular weight of the protein and also the frictional coefficient. So, just a few words on this frictional coefficient, because this is an important parameter and which gives us information about the shape and size of our protein. So, assume that you have a protein, we have two proteins of exactly the same molecular mass. So, one protein is like a sphere and the other protein is like a disc like this. So, if the protein which is spherical is moving through the solution, the frictional force on this will be much less because the surface area is less. But the protein which is like a disc, and if it is moving through the solution, the frictional force on this protein will be much higher because the surface area is higher. So, this number gives us information about the shape of the protein. So, using AUC we can determine the shape of the protein along with molecular mass and also some other parameters. Another very important experiment that is used very frequently to analyze protein samples is circular dichroism. So, it can be used to determine whether a protein is folded or denatured, because the signature of a folded protein and a denatured protein are very different in CD. We can estimate the secondary structure composition of a protein, that is the percentage of alpha helix, beta strand and random coil. But the limitation of circular dichroism is that we do not get any residue specific information. So, using CD we can determine whether our protein is folded, and if it is folded, what is the secondary structure content of this particular protein. If you want to determine structure in high resolution, then there are two experiments. One is X-ray crystallography and the other one is NMR spectroscopy. So, both these experiments need a lot of expertise, take a lot of time, but they provide you three-dimensional structure of the proteins with atomic resolution. So, you will know exactly where each atom is in space. NMR spectroscopy also provides you some more additional information, such as the internal dynamics of a protein. So, a protein is not a static molecule. Different parts of the protein can fluctuate at different time scale, and we can get information on those time scales using NMR spectroscopy. Finally, if you are also interested in the functional aspect of protein, then you will have to do some functional assays. If it is an enzyme, then specific assays can be designed that depends on the reaction that is catalyzed by that enzyme. One such example is shown here. Alpha chymotrypsin is a protease which cleaves after big bulky amino acids such as tryptophan and tyrosine. So, this assay uses that property of alpha chymotrypsin, and it cleaves this peptide bond between N-benzyl group and a tyrosine. So, we have this tyrosine and then followed by a ethyl ester. So, it cleaves the bond after the tyrosine and between the ester. So, if we add this, what we get is N-benzyl tyrosine ethyl ester plus ethanol, and the product can be monitored at absorbance of A256 nanometers. Remember that tyrosine, its maxima is at A280. So, at 256 it will give us very less absorption, and we can always subtract the background. so that we can monitor the product formation at specific time intervals, and using that we can determine the activity of the enzyme. Similarly, binding assays can also be developed for proteins, and depending on whether the protein binds a small molecule or it binds another protein or it binds nucleic acids, different assays can be developed. So, we have one lecture where I will discuss about these protein ligand interactions and the experiments that can be done for protein ligand interactions. So, again the references are all up here. Thank you.